Hello, can you hear me?
So today we'll talk about diagonalizable linear maps. So just as a quick refreshment, in 223, the matrix is diagonalizable if you can write it in the form P inverse dP, where so A diagonalizable matrix A. Where D is diagonal. That's all you need. So there's nothing special about P. So we'll do the same trick, right? We're working with a linear map, V to V. We're gonna come down with coordinate map. Now we have a matrix B, TV, and we're gonna get this guy to be diagonal and then come back. So we're gonna push diagonalizability down to the matrix. Right. But definition-wise, so here's the definition, is that your linear map is co-diagonalizable if you can find a basis of eigenvectors that are also a basis for V. So let me ask you a stupid question. Take R2 and take the basis to be 1, 0 and 0, 1. Can you give me a map whose eigenvectors are these guys? I just want to say, yeah, just the identity. So this is if and only if. I don't know, whatever, doesn't matter. But anyways, you get the point. There's a, but here we're interested in the reverse, of course. You start with some map, you have a collection of eigenvectors, Vk. So Tvi is lambda I V, right? And then their span gives V. So it should be N. Anyways, yeah. Okay. So if that's the case, you call it diagonalizable. Let me remind you, last time we looked at this matrix, 1, 1, 0, 1. Its eigenvector was, if you remember, it was 0, 1. So he had only one eigenvector. So, but you need two. So not enough to span R2. Only had one eigenvector. Okay? So that's another way to check. You find your eigenvectors and you're like, oh, this doesn't give me the space. Because it's hard to say it's not diagonalizable if you use the other definition from 2 to 3. Because how would you prove that this is not the case? you will have to like prove that there is no such matrix P that maps you to D. How would you do that? Right? I mean, it makes no sense. Whereas here, you find your eigenvectors and they don't span the space, so done. All right, but we have to come back to 2 to 3. So let's do that. Two matrices are called similar if you're able to write them in that form for any matrix P. There's nothing special about it. We're not going to do more fancy stuff. So P is any matrix. Usually we take it to be orthogonal. Yes, all right. So this is 2 to 3. So I'm not going to do too much of it because I want to do the tricky proof of multiplicity. So this one I'm just going to, I type the proof for you and we're just going to reference the result. So it just says that T is diagonalizable if the matrix representation can be written as P inverse dP, where D contains the eigenvalues. Right? So this goes back to 2 to 3, namely that this is the case if and only if epsilon T of V1 to Vn are a basis for V, right? So, right, we got a diagonal matrix. So this was our example. But I talked about it last time. Yeah, so let's talk a bit about the proof. I won't go too deep into this. Yeah, since you are diagonalizable, yeah, I should have done it already. It's fine. That's not, I don't want to go into this. So I wrote the proof for you because I really want to do the other stuff, which is much harder. This one, you just use a 2 to 3 material. You're just going to compute the linear map of the eigenvectors. So let's not, if we have time, we'll come back to it, but the other theorem is much, much harder. All right. We had to make choices. I mean, so she told us to drop some stuff. All right. Okay, let's see. So this is the hard one. You're going to see this many times. You didn't do this in 2 to 3. There was only a last page comment about it, but here we're going to prove it. So, a linear map will be diagonalizable if you have the following result. The geometric multiplicity equals the algebraic. So if you have this for each I, you're done. Okay. Why is this easier? Let me see. Okay. I mean, still here you have to compute the eigenvectors, so you can't get around that because you need to know how many linearly independent vectors you have here. So dimension of span of V1 to Vni. So you need to know that. But at least this one is easy because you just compute the characteristic polynomial. Yeah, okay. I guess, okay, here's why this is cool, because you don't have to show that these guys are a basis. How about that? All right, so you don't have to like sit down and prove that these are linearly independent, that they are, that their span spans the space. Okay, So if you just prove this using our dimensional results from 2 weeks ago, you get it for free that you will get for free that epsilon t is a basis for V. So remember, this is tricky to prove, right? You have to prove Li and span. But we have a proof of this stuff using dimensions. So, if W is inside V and dim W is dim V, then W is V. That's basically what we're going to do here. That's the argument. So just by having this dimensionality, we're going to get it. All right, let's start. So this is a very long proof. So we'll go step by step. In our previous example, we from yesterday, we found the eigenvalues 1, 2, 3. I have it here. So, right. So we had this map. We had this map T, and this is on a space of polynomials, P2R, P2R. And we wanted to find its eigenvectors and eigenvalues. So we did that. We found one of them, this guy, which corresponded to minus x plus x squared. And yeah, anyhow, so you have 3 eigenvalues and they each have one eigenvector. So dimension of E lambda I is 1. And I think I have the polynomial somewhere. Anyways, I mean, you can see it from here. This is your matrix. And if you take its determinant, you get 3 minus lambda. Remember, I talked about this. Okay. So the determinant of this is 3 minus lambda, 2 minus lambda, 1 minus lambda, which all have multiplicity 1. Okay? So multiplicity equals the geometric multiplicity. All right. Right. So anyway, yeah, let's do it. So this is section 4.2, and it's really mainly about this result. So it's a very, very long proof. So we'll go step by step. Okay. All right. First thing, we need to show that if I give you some eigenvectors and they have distinct eigenvalues. So in our previous example, we have t minus x, x plus squared is 1 times this. And what was the other eigenvector? I think it was 1 plus x, minus 1 plus x. And then t of minus 1 plus x is equal to 2 times minus 1 plus x. So the eigenvectors here are v1 minus x plus squared and v2 minus 1 plus x. And we would prove that they are Li. Okay, which is would be nice to have that like a few weeks ago to show that these two are Li. I mean, imagine, look at this. How would you prove this? You have to like put them together, compare coefficients, right? Remember, we have a minus x squared plus b minus 1 plus x. You set this to 0, you solve the system, blah, 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 blah. Here you get it using this result. So that's what we're going to prove. Right. So let's do the base case. Meaning you start with 2 eigenvectors. So TVI is equal to lambda IVI. And we do it, yeah, so you start with the linear independence assumption. condition, right? This equation, and we want to show that A1 is equal to A2 is equal to 0, right? All right, so you assume otherwise so that we can divide. So let me write this down. So assume otherwise, meaning that A1, without loss of generality, A1 is not 0. Okay, let me write without loss of generality. So we can divide. And then, all right. And then we can evaluate TB1 in 2 different ways. So one way you use that it's an eigenvector. And the other way you use your formula star. If you use the eigenvector, you get lambda 1v1. If you use star, the dependence, you get lambda 2v1. Okay, very happy. Then you bring it to the right, so you get this. So how do we finish from here? Yeah, I know you know. Let me see if other people are. Yes. How do we finish from here? What's the punchline? You see? I need to see if other people follow. Yes. Right. So by definition, an eigenvector is a non-zero vector. Okay. Otherwise, it's trivial, and we don't care about it. So V1 is eigenvector. So V1 is not 0. And you get a contradiction because lambda 1 minus lambda 2 is not 0 because they're distinct. And so contradiction to A1 being not 0. Okay. So A1 and A2 are both 0 because you could have flipped around and do it for A2. Good. So, all right. So we got our independence for the base case. Now let's do the general. So how does induction work? You assume now that your statement is true up to n, meaning that if lambda 1 to lambda m are distinct, then V1 to Vm are Li. Okay, so that's your inductive hypothesis. Prove it for n plus 1. Okay. So now we study the next case, n plus 1, and we want to show that B1 to Bm plus 1 are all 0. All right. So what's the trick? So you compute both sides and you use the eigenvectors. So T Vi is lambda I Vi. Okay. Step by step. All right. Then, so this is the proof in the book. So if you find a better one, please let me know. It's kind of complicated. Then you multiply both sides by the last eigenvalue. So let's see what they mean by this. So you do lambda m plus 1 times B1 V1 all the way to minus lambda m plus 1 of what? Bm plus 1. Vm plus 1, which is equal to 0. Okay? So we multiply this by minus lambda m plus 1. Then you take this equation and you add it. I wanted to say 2 here. I don't know why I said 2. 2. So you added to 2. So you have, where is it? Let me go upstairs. So you have this equation and you add it to this guy. All right. So you have, yeah, so you just match the coefficients, and the last guy is 0 because this was just bm plus 1, lambda m plus 1, vm plus 1 minus from here, you added the minus of it. Okay. So that's the trick, right? Because we want to kill the m plus 1 guy to go back to m. Now we're left with m terms. These are m terms. So we can go back to our inductive hypothesis. Because we know it up to m. We don't know it for m plus 1, so let's kill the m plus 1. So we killed it. We're back to m. So let me ask you, I have it here. Yeah. So how do you finish from here? What's the punchline? Yes. And then what's the contradiction? So the distinctness. So this is a contradiction to distinct. Lambda I is not lambda j. Okay. So now we have independence. So yeah. All right. So one powerful implication, this is 4.25 in the book, is that the eigenspaces form a direct sum. So this is homework 2. Yeah. And why do we need this direct sum? Just as a prelude, we proved there that if you take their direct sum of the E lambda I, you get back their sum. So E lambda I, and yeah, we'll come back to this, but this is the result we need. And from here, the criterion will be like 2 steps away. I mean, this is the meat over here. The potatoes come in. All right. So let me explain the notation because it's quite again, this is from the book. And it's a little bit hard to see what they're doing. So you fix an eigenvalue, let's say lambda 1. You have an eigenspace E lambda 1, and this guy is spanned by some vectors, v1, 1, all the way to v1, n1. Okay? Let's see. What's a nice example? I mean, just I know, okay. Here's a stupid example. Take your map to be 1, 1, 2, 0, 0. All right? Can you guess what's E of 1? I don't know. I mean, this is hard to guess. Yeah. Is that okay? You can. All right. Let me How do you check it? So you can just plug it in. If you plug it in, you will get 1 times 100, and same thing for 010, and for the last one 001, get 2 times. Okay, so this guy has 2 vectors, and E2 has only 1, 001. So in this crazy notation, this will be V11, and this will be V12, and this will be a V21. Okay, let me go to the notation. All right. Does that make sense? Okay, fine. Anyhow, so yes, so for every eigenspace, you have some vectors, and there could be more than one, like in this example that we just did. And yeah, you assume that they're Li. This is kind of a redundant assumption. If you can tell me why, that would be cool. Why, if you have that, there's exactly the dimension of them, you get Li. Okay, so we proved this, that we proved the result, namely that if a set is a spanning set, so spanning S, the cardinality of S is bigger or equal than the basis of the, let me just write dimension. Dimension of E lambda. But here we have that they're exactly equal, and we prove that if then S is Li. These are old results. We can go back to them if you want. All right. The big result is that if you put them all together, so the one from before, we have 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? This was E1, this one was E2 span. That in fact, all 3 of them together are still Li. Okay, that's not obvious, but that's the result. So we know that this and this is Li from what we proved before, but now we're saying that if you put all of them together, I mean, it's kind of obvious, right? Because each of them is Li, and then you use the other result where across different eigenspaces they're Li, right? That's what we just proved, right? That this guy here and this guy here are Li. So we just have to put it together mathematically. Right. So, and they form a direct sum. So let me do this with you. Yeah, I just talked about the Li. So let me make a simpler question. Suppose V is the span of V1, V2, and W is the span of W1, W2. How can you get the W1, 2, V1, V2 are Li all together? How can you get that V intersect W is just a 0? Even from the chart, you guys can speak up. How would you prove this? Assume they're in some bigger space U, like they're both in some bigger space U. So it could be like R6, and you take like R2 and R2. Yeah. Okay, you got it, you got it. So if X is in here, then X computed as, perfect, perfect. So C1, V1, C2, V2, but also A1, W1, A2, W2. Put them all together. And you get C1, V1, C2, V2, minus A1, W1, minus A2, W2, all equal to 0. By Li, you get that they're all 0, which means that X was just a 0 guy to begin with. So that's how you get direct. That was the assumption for direct sum, right? That's all you need. So once you know they're non-intersecting, you can write down direct sum, and you have the dimension for it. Right. So that's why you get direct sum from this. So that's why we'll come back to this explanation. All right. Let's start with results. So we want to prove Li. So we put the entire collection together, right? So let me remind you. We want to prove that this entire collection is Li. So we write one long equation. Right? So we put them all together. Right? Is that okay? Like, yeah, so, you know, each of the stuff in the union is one of the sums. So I just broke it down. I could have written like in the book, like one long thing, but I think it's a little bit clear that this is the guy from the first eigenspace, you know, or the span, and this is the guys from the last eigenspace, okay? Yeah, yeah. All right. And you want to show that the coefficients are 0. All right, let's do it. It's very quick. So yeah, the way I wrote them is very suggestive. So you call this guy W1 and you call this guy WK. So let me ask you this just to see if you're following. How do we know that the summation is inside the eigenspace? Like I wrote in. How do I know this? Yeah, I know. But okay, how? Because you asked it yesterday. So why is it a subspace again? Yeah. Yeah. So this guy was the kernel of T minus lambda M identity. All right. So they each belong to E lambda M, and then we just rewrite this guy in this short form. Nothing fancy here. But right away we're done. Let's see why. So again, these are separate elements from each of the eigenspaces. Let me do the 1 plus 2 case. Can you tell me why we get that they're actually both equal to 0? This is an exercise in definitions of linear independence. Right. So, how do you say? Because the book is not all right. I don't know how to say it. Linear independence is for non-zero vectors. Like there's this little assumption, non-zero vectors. So, how do I say this? So we just proved that if lambda I are distinct, then the V corresponding VI, not corresponding, the non-zero VI are Li. right? That's what we just proved before. So if you take the counter positive, very weird. The counter positive says they're either dependent or zero. Okay. So because we, this is very annoying. All right, let me see how to say this. Yeah, let me write it this way. So either they're linearly. So there's two. Okay, you have two cases: linear dependence or linear independence. But the linear dependence splits into two. Either you have that they're all zero, or you have that you can write them in a combination. We just showed that this cannot happen if this cannot happen if lambda I are distinct. Anyways, if we, I'm overcomplicating stuff. So if you ever prove linear independence and you write something like this, you can jump right away to that. Because part of the assumption is that they're non-zero. So the only way you can have dependence is that they're zero. There's no way around. I mean, we can go over this more in detail. So it's just the tricky thing about independence, that you need the non-zero assumption. All right. I think I overkill this topic. So fine. So you get that each of them is zero, because if they weren't, you know, okay, let me do it in contradiction. If they weren't, you will have this, but this is linear dependence, which contradicts our previous result. How about this? Implies linear dependence, which implies this. Is that okay? Everybody happy? Yeah, yeah. I think this is cleaner. Better argument. All right. Now, if you have the W1 is zero, how do you finish from here? No, we know that they're all zero. How do you finish the result that that these coefficients are all zero? Yes. Yeah, but what was the assumption for the V's? No, but I mean, you can have like the same guy, like 1, 0, 0 and 2, 0, 0. They can both be eigenvectors. So what was the extra assumption? Yeah, that's all. That's all. I know my questions are redundant. So like, yeah, that's all. Just to make sure you're following. So yeah, but V 1 to V 1 N1 are Li. So you get that their coefficients are all zero. So A 1 R. So let me put it here. So then the coefficients are all zero for it. What's my notation? So 1, 1, and then 1 and 1. All right. So you get that all the coefficients are zero, because you got that each of the W's is zero. Is that okay? All right. So just at least to understand the punchline, The punchline is if you have a bunch of eigenspaces and you know their bases, you can put their bases together in a way that they don't overlap. Because that's the problem, right? You don't know necessarily that they intersect or not. So you can form a nice direct sum. Okay. Yeah, except the zero. Yeah, that's right. Yes. All right, so now we can do the punchline argument. Right, so the criterion was, let me put it here. So, yeah, we'll talk about this. So in your book, they have the following criterion, this guy over here. So if you show that the sum of the dimensions is the whole space, then you get that T of B is diagonalizable. Okay? So that's the criterion in the book. So let's prove that. And we're going to use the definition for diagonalizability. We're going to show that if you take all the eigenvectors of T, remember that crazy collection that we had of the V I, so this is V1 I, V, and I. So this is what we call epsilon, and these are all possible eigenvectors. Okay. So we're going to show that there are bases. Want to show basis for V, the entire space. If we do this, is that okay? Let's do it. So in your homework, you show that if you have the dimensions to be, so what did you do in your homework? First, you showed that if you have a direct sum, the summation of the dimensions of these guys, the summation of the dimensions is equal to the dimension of the sum. Yes, good. But now this is the assumption, okay? But you know that this guy is equal to dim B, all right? How can you, okay, let me just do it. But you also know that this guy is inside V. Okay, so this is one fact, this is a second fact. You put them together, so you get that these two are equal. Okay, so this is homework. This was in your book. This implication was in your textbook. And I think I did it as well in class. Okay, so we have this result here. Now let's finish. So can you tell me how can you go from here to show that epsilon t, of all these eigenvectors, is in fact the basis for V? So how to finish from here? Yeah. Perfect. That's it. That's what I want to hear. So take this epsilon t. This is a set inside V, and we prove the following result. We prove that this is from before. Epsilon t, that if you have this equaling dim V, and epsilon t is Li, then epsilon t is a basis for V. Okay. So how do we know this? I'm just testing to see if you understand. How do we know that the cardinality of the set is equal to DV? I don't know. Yeah, go ahead. Right, so this Ni here is just the dimension of epsilon lambda I. So if you just count them up in this union, you get that epsilon t is equal to the summation of dim E lambda I, which by assumption in the result, it's dim V. So that's how you get this. And that's it. Yes. You even countable works. We never used finite. You just have to be able. I mean, there's a lot of things here like this sum converging and blah blah blah. But yeah, but as long as you have countable, so you can actually sum, it's fine. Yeah, you just need countable. We never used like. Okay, what else? But we want to make your life even easier. So proving this summation of blah blah dimensions is equal to the whole space can be tedious. So here's the result we're going to prove. We're going to prove that if dim E lambda I is exactly equal to Mi, then yeah, T is diagonalizable. All right, maybe I should do the punchline here first. Yeah, so let's do why this is the case. So let me ask you a question. Why is it that the sum of the algebraic multiplicities is equal to the dimension of the space? So let me remind you, P lambda, the characteristic polynomial, is equal to this. Okay. Why do we get that their summation is the whole space? What's the theorem we're using? Yeah, sure. So that will give you inequality. But why does it give, why do we actually have equal? Okay, so yeah. No, it's just I'm not sure which version you've seen, but the fundamental theorem of algebra says that every nth degree polynomial has exactly n complex roots with multiplicity. Yeah. So, which is exactly the statement we just wrote. Okay, I mean, yes. Oh, right. So, yeah, this is interesting. So, let me see. So what is characteristic polynomial? We defined it as P lambda as determinant of the matrix T minus lambda I evaluated over some basis B over V. And good. And so let me see. Right. So this guy has dimension. This has degree. This is a polynomial. of degree size of B, because this is a matrix. This is a B by B matrix. Okay, and then how do we get from here that in fact is degree dim B? How can we get it? Yeah, the cardinality of the basis is an invariant. Okay. So we proved before that B is equal to dim V for any basis B. Yeah, exactly. Which I'm pressing Camellia to put it in the homework because it's a travesty. You have because how do you know the degree unless you use the formula? I know you did row reductions. You told me you did row reduction, right? But you don't have a formula. Sorry? Okay. So we'll continue tomorrow. Thank you.